Welcome to video 3. This is the second example of finding concavity, whether a function is concave up or down, and any points of inflection. With example 2, we're given a trigonometric function. However, be very careful. Let's read what they're asking for and what we're given. It says find the open intervals where the function g of x is concave up or concave down, and find any x values where g of x has a point of inflection. Give a reason for your answer. However, we're not given g of x, we're given g prime of x. But remember we said in order to find concave up or concave down, we need the second derivative of the function we want to find the concavity for. So I need the second derivative of g. I already have the first derivative, so I really only need to take one more derivative and then I'm done. I have the second derivative of g. So if, just to clarify, if I wanted to find the concavity of g prime, then I would need to do two more derivatives, get the third derivative of g to describe the concavity of g prime. But I want to find the concavity of just g. So take one derivative, take another derivative, that leads us to the second derivative, and here we get to take the second derivative. In the first part, I have a chain rule. I have a chain rule because remember that this is really sine x squared. So the derivative would be 2 sine x times the derivative of the inside, which is cosine x, plus take derivative of cosine x, and that's negative sine x, so I think I'm just going to write it as minus sine x. That's my derivative. Now, it's really looking a little complicated here, so I notice that both of these terms have a sine x in common, so I'm going to factor out a sine x, and I'm left with this. Great, that actually works out because now I have a multiplying situation here. I have two factors that I'm multiplying. And if I want to set the second derivative equal to 0, then I can say g double prime is equal to 0 if, well, if the first thing is equal to 0 or if the second thing is equal to 0. Right? If the first factor is equal to 0, 0 times anything in the parentheses makes the whole thing go away. Or if the parentheses is equal to 0, anything times that will make it equal to 0. So now it's time to think. And we're gonna keep the domain that was put in example 1. Remember that I circled. We're gonna use it down here and say we're only gonna be worried about 0 to 2 pi. Okay. So what are some angles that when I take the sine of that angle, it equals 0? And it has to be between 0 and 2 pi. Uh-oh, I think I lost it. So what angle, when I take the sine of that angle, gives me 0? Well, one of them would be 0. And the other one would be pi. So therefore, x equals 0 and x equals pi. These are the two values that would make this equal to 0. There are more. However, we're only worried about x values in between 0 and 2 pi, so these are the only ones that would work. Now wait, was it a closed 2 pi? It was a closed 2 pi. Okay, so then we have to include 2 pi as well, because it says it includes 0 with the bracket, and it includes 2 pi with the bracket. So 0, pi, and 2 pi. My bad. To figure out the second part, let's see. Well, I need... All right. It disappeared again. I think my screen is very sensitive, and it picks up things that I don't intend to do for it to do. Let's solve for x. Well, you would add 1 over, divide by 2. So now I'm asking you the cosine of what angle equals 1/2. The cosine of what angle equals 1/2. That would be at pi over 6. No, pi over 3. My bad. Pi over 3. Or it's also positive 1/2 at 5 pi over 3. So at these two angles, when I take the cosine of these angles, it equals positive 1/2. Again, there are others, but within the window of 0 to 2 pi, those are the only ones that work. Great. What did we just do? Well, we helped create our dividers of our sine chart. So I go to my sine chart and I say the x values that we're going to need are 0, although there's nothing going to be to the left because we start at 0, pi over 3, pi, 5 pi over 3, and 2 pi, but there's nothing going to be on this side because our our domain, I guess, is set from here to here, and that's it. So my answers have to be in between 0 and 2 pi. So let's pick some values. Now, when I pick values, remember what we're checking is, does it make the derivative, the second derivative, positive or negative? So in this first part, let's say I choose, let me use this color. Let's say I choose pi over 6. Pi over 6 is between 0 and pi over 3. And pi over 6, if I substitute it in for the first part, sine of pi over 6 is 1/2. And then cosine of pi over 6 is square root of 3 over 2 minus 1. So this is positive. These are going to cancel, and I'm just left with the square root of 3 minus 1, and that's positive. So therefore, these are positive in between these two. Oh, by the way, why are these special? Because the second derivative of g, so g double prime, is 0 at all of these x values that I had initially written down. But I checked the one in between 0 and pi over 6, and it came out positive. Great. Let's choose another one. So between pi over 3 and pi, well, what about pi over 2? Okay, so sine of pi over 2, that would be 1. That's positive. And then cosine of pi over 2 is 0. But 2 times 0 is 0 minus 1, that's negative. And a positive times a negative is going to give me a negative. So all of these guys are negative. And we just keep checking points like that, right? It's not a, I'm going to use 3 pi over 2. And if I use 3 pi over 2, sine of 3 pi over 2 is negative 1 times 2 times cosine of 3 pi over 2 is 0 minus 1. 2 times 0 is 0 minus 1 is negative 1 times a negative 1. That's a positive 1, and therefore all of these are positive. And I think you can guess what's going to happen next, but we'll check just in case. Let's pick a number over here like 11 pi over 6. We could also, by the way, we could also choose 7 pi over 4 if you want. That's maybe a little bit better. I don't know. Sine of pi over 4 is square root of 2, negative square root of 2 over 2 times 2 times the cosine of 7 pi over 4. The cosine of 7 pi over 4 is square root of 2 over 2 minus 1, because that's part of the formula. Well, this outside factor is negative. These are going to cancel, and I left with a square root of 2, and the square root of 2 is bigger than 1, so square root of 2 minus 1 is positive, and a negative times a positive will give me a negative. Whew, that's a lot of unit circle thinking. But we made our sine chart. What does this tell us about the original function? It tells me that in between 0 and pi over 3, it's concave up, but in between pi over 3 and pi, it's concave down, then it's concave up, then it's concave down. So we're going to say that G is concave up on x values that are between 0 and pi over 3, or x values that are between pi and 5 pi over 3. And I know this because the second derivative is greater than 0. It's positive. Very similarly, we're going to say G is concave down on, well, between pi over 3 and pi over 3 and pi, or in this other section, between 5 pi over 3 and 2 pi. And I know this because g double prime is negative, less than 0. By the way, if you write the word negative, g double prime is negative, it is acceptable. I'm using the symbols just because it might be a little bit faster than writing out the word negative. I think that might be a little bit faster. Save yourself a second or two. Great. But now the last part, does it have any points of inflection? Well, yes, because it changed signs here, it changed signs here, and it changed signs here. So I'm going to say G has points of inflection, or inflection points, if you want to write it that way and save yourself the middle word. Points of inflection at x equals pi over 3, x equals pi, and x equals 5 pi over 3. And the reason is because G double prime changes signs. That's it. Since I know that the second derivative changes signs at those x values, they have to be points of inflection. Questions about that? I guess you can't ask them, but you can bring them to class next time and we can answer them. And that's example number 2. In the last video, we'll look at some graphs. They might go a little bit faster where maybe we don't have to do a lot of calculation, but we'll interpret some graphs and use those in order to find the concavity of the function that they're asking for.